Hello everyone, I am Zhongyu from the storage team of Alibaba Cloud. Now we are gonna present our work, Ransom Access Memories, Achieving Practical Ransomware Protection in Cloud with DeftPunk. Okay, first, let's review some basic information on ransomware attacks. Assume that the user has an important file in a virtual machine, for example, the txt file here. And if the user uses a weak password, a hacker can use this vulnerability to install ransomware on the virtual machine. The ransomware will encrypt the txt file, and then the user can no longer access it unless paying a huge amount of money. Even that, it is not a good ending. In reality, we have seen that there is a double-digit increase on both the number of instances or also the amount of money in failed reports. In Alibaba Cloud, we have witnessed more than 1,000 attacks in Q3 of the year 2022 alone, and there is a triple-digit increase over the previous quarter. So, in short, ransomware is rampant in cloud. Currently, there are several defense mechanisms aimed to defend the ransomware. So, we categorize the mechanisms into 4 categories. On the top level, it is important that the user should be aware of such attack modes and install the antivirus software. Secondly, they can also patch the OS for better protections, like the work unveiled at USENIX Security 16. And then, for cloud block store providers like us, the user can ask us to perform scheduled snapshots. So, if there is an attack, the user can roll back to a previous checkpoint to avoid the files from being tampered. And finally, we have seen that there are hardware protections that can detect the attacks and roll back the data to normal. However, the mechanisms are not working in the cloud, at least in our scenario. First, the users are the first and often the weakest defenses. They can and are still failing to phishing attacks using weak password or fixating outdated software. The patched OS is also not a good solution because users still tend to use either official or their own OS images, as it is easier to migrate what they already have been doing to the cloud. Thirdly, even though there are scheduled snapshots, but if you want to make it too frequent, let's say every minute, it will cost you a lot of money, maybe a lot more than subscribing the virtual disk itself. Or, if you want to take a less frequent way, for example, on a weekly basis, you are running the risk of having data loss in between. Finally, we have hardware protection. However, those are still on the POC stage and may require a lot of time to land on markets. So, existing solutions do not work well. Now, let's see how DeftPunk solves this. Before we start, let us just first understand how a FTL-based solution defends the ransomware. The key idea is simple, and there are 2 parts. First, the ransomware, as we said earlier, has this fixed procedure of read, encrypt, and write back to the same location. This can lead to a strong IO pattern on the flash page, which can be caught by the FTL in a simple way. Second, in the flash-based SSDs, data are not immediately deleted. Rather, they are still there for a period of time until reclaimed by the garbage collection. So, after the FTL detects an attack, it can simply roll back the data to a previous version to notify the attack. Fortunately, our Cloud Block Store shares the two features as well. First, our Cloud Block Store offers virtual block devices to users. So we decided to check whether ransomware and normal apps have distinct difference on logical block address access patterns. As we shown here, we can clearly see that ransomware tends to have the exact same amount of read and write due to its read, encrypt, and write back procedure. On the other hand, the normal apps can have rather varying behaviors. So we can leverage this feature for detection. Moreover, our block store, like many other storage services, is built on an append-only file system. So, in this case, the user's file in our cloud store is multi-version by nature. For example, just like the txt file here, when user modifies it, the older version could be not directly deleted, but wait to be reclaimed by the GC in the near future. Therefore, after we detect the attack, we can roll back the user's data to a previous version for protection. However, this is simply too good to be true. In practice, we have encountered three major challenges. The first challenge is that SSD-based solutions are using simple features. For example, the control right after read IO here. But if we replicate this practice, the results can have high false positives and negatives. This is because the SSDs have a relatively weak processing power, so they choose simpler features. But the cloud workloads can be varying, and therefore cannot be easily differentiated by the simple features. To overcome this, we have extended the features. First, we found the equivalent amount of read and write in ransom. It is because massive write after read IO leads to this distribution. Then we realized that the ransomware, or in order to create a huge impact, it will touch so many files, so it will access a wide range of LBS. The normal application instead are usually focusing on certain locations. Thirdly, in order to create a huge impact, the ransomware will also pay a special attention on the important regions. For example, the first 100 million bytes of LBA, where metadata are usually located. Based on above three observations, we have enriched our features. Now, with the full set of features, we, however, discovered that we are not able to use this in practice, because simply use these features, while did give us a high precision and recall, they took too much resources to finish. So in that case, we are running the problems of balancing the speed and the accuracy. To solve this problem, we developed a two-layer cascading model. The first layer aims to fast filtering. In this case, we only include older one features and use the fast model, namely decision tree. If the IOs are flagged by the first layer, we will push them through the second layer, where we have features that requires older login computing complexity. Moreover, we also use an advanced model, namely XGBoost, for beta accuracy. We designed this two-layer model because most of the devices are not being attacked by ransomware. so we just need to run layer 1 in most cases. Even with the accurate and fast detection, we choosing which point in time to roll back can be tricky. This is because the detection will need to be triggered after several IOs. If simply choosing the start of the detection to roll back, this can cause potential data loss. Therefore, in DeftPunk, we create a pair snapshots before and after the attack, and further preserve all write logs between the snapshots to avoid any data loss. This is doable as our storage backend is multi-version by nature, so we can create a pre-attack snapshot after we detect a ransomware attack. Put it all together, it will have an IO collector to collect our traces and speed the records to samples and feed them to our ransom detector. The ransom detector extracts the features and brings them to the two-layer model. The ransomware, once the ransomware detector detects an attack to be found, we are using a data reserver to do the check on it and redo based on our prepared snapshot and write logs. Here is the evaluation. For the evaluation, we have our platform and two sets of traces. First one is from real-world normal traces on the 16 typical cloud applications. And we also have 13 families of ransomware on the 6 OSs and 5 applications in total. We have mixed them to achieve near 400 setups. The result shows that overall we have nearly 100 recall and 98 precision. The only case we have a low precision is because the user has exactly the same behavior as ransomware. For example, encryption. But it's not an issue because when we detect and then notify the users to perform rollback, if the user thinks this is a false positive, he can simply choose to ignore it. Actually, we have the zero-shot performance with excluding one ransomware from our training. It is glad to see that we can still be able to detect the virus and the results showing that they are high recall across all families, except one case, ransomware number 12, and that is because the ransomware is not to encrypt the text files, and that trace we are building happens to contain much of this type of data. You can read our paper for more evaluations. Now, let's end with a discussion. Beyond DeftPunk, we want to raise the awareness on the ransomware detections. First, this is a cat and mouse game. During our development, we have seen new trends like WannaCry, which intentionally slow down the encryption procedure to lower CPU utilization and try to avoid detections. This can be called by the DeftPunk since simply slow down does not change the patterns. We still want to infer that the hackers could and would alter their patterns, like directly destroying the data or writing the encrypted data to some device else. To better adapt to these changes, we believe this requires joint effort from the community. Therefore, we share our dataset to the public to facilitate and improve the detection. There is a never-ending arms race. Well, that concludes our presentation. Thank you.